So logical neural networks, this is a paper that has come out of IBM research. And this is going along with the notion of let's have the neurons of the neural network align directly with the logical syntax. So unlike when we get to logical tensor networks in the next lesson, there's no like crazy embedding or vector structure representing individual logical propositions. They're actually directly to the neurons. That's kind of the big intuition. All right, so here's how we'll organize the chat today. I'm going to start with just a couple slides that will show some very telling passages from the paper to communicate some of the central ideas. But that's just to give you a feel for what's to come, and then we'll start to get to the basic setup. We'll talk in turn about the underlying logic framework these guys are using, how they're doing inference, which essentially is the forward pass, and how they're training the model, which are the three big pieces. And then we'll get more in depth on inference and learning, and then we'll end with some concluding thoughts. So here's some of the central ideas. So we spoke before of Markov logic networks, and as well as probabilistic soft logic. And so the authors of the logical neural network, they view that as kind of the starting point or the baseline they want to compare against. Logical tensor networks was very contemporary to LNNs, but they do talk about that as well. But I think these papers were maybe less than a year apart. I think the LTNs was the first conference paper, and these guys did something about a year later. And so the key thing is that, hey, if you have a weight associated with a logical rule, but then you can't decompose that rule, then you lose a lot of things like explainability, modularity, sort of the traditional things that people in logic programming always tout as kind of the main reasons for doing this sort of stuff. And so they said, what they wanted to propose was, hey, the network structure of your neural network is going to correspond directly with the syntax. And the way they do this is they will use a syntax tree, and I'll try to go through that. The other thing that they talk about is they talk about what they'll term as the closed world assumption of things like MRFs, or anything that's assigning a single scalar value to logical statements. Because what they're essentially arguing is that if you assign a scalar, such as a point probability, to a logical statement, what you're saying that if I say atom A is true with probability P, maybe I'm then implying that not A is true with 1 minus P. And there's no chance for any kind of ambiguity in between. And so what they use is they actually use bounds on the confidence interval as opposed to scalars. And I actually, personally, I really like this idea because it allows you to deal with noise better for the learning side. And also, I think that I like to think of assigning truth values in logic as something of you, instead of getting more true, you should think about becoming more certain. And so the view of saying, hey, I have a scalar, well, that's sort of implying that everything is false. And as I get more data, it becomes maybe more true. You run into problems if you want to reason significantly about negation in such a framework. So if you're doing probabilistically, then you start having to do things like generate a bunch of worlds and things like that. If you're not, then you lose expressiveness because everything goes from being false to some level of being true. Yeah?
So if A has an upper bound and a lower bound, the truth values, does not A have 1 minus the upper bound and 1 minus the lower bound?
Yes.
Okay.
Yeah, and so the idea is that the you start out with everything being uncertain. So you have assume a bound of like 0, 1. And then as inference goes, that bound collapses. And it can collapse to 0, 0. It can collapse to 1, 1. It can collapse to something in between, like 0.5, 0.5. But if it collapses where the upper and lower are equal, then there is no uncertainty at all there. So, and if you would use a probabilistic interpretation of that, you could think about a wider bound is essentially implying I have some second order probability distribution. Now that might sound really nerdy, but it's not really, because when you look at things like election polls, you always see error bars, right? Second order probability is just a way of communicating uncertainty about the probability. Now, the LNN guys, they do say there's a probabilistic interpretation of their confidence bounds in the paper. Admittedly, I do take that with a grain of salt, and we can have this discussion about probability versus confidence in like a whole other lesson if we wanted. We won't do that today. For now, we'll just focus on confidence and the fact that uncertain, you have a 0, 1 bound, and it's going to collapse as you get more certain and do more inference. So, so the other thing going on here is discussion of bidirectional inference. And so what this means is that there's this idea that's kind of prevalent with other frameworks that you start with individual atoms and then you see if a bunch of formulas are true or false. What they're saying here is bidirectional. I'm given a bunch of formulas. I can see from an initial set of atoms how true those formulas are, but I can also go back the other way. And so so again, this is kind of, they tout this as an aspect of their framework because we can, it just gives us just more expressibility. And we'll kind of see how this works in both the, we both see the layout of the neural network as well as their algorithms for inference. All right, so let's get to the basic setup. All right, so the underlying logic is fuzzy. And so everything has these bounds as I discussed, these LU bounds. And so, and also this is a first order logic. They show most of their results in the main paper for the propositional case, but they actually have a whole lot of supplemental materials that get into certain extensions for first order logic. That it's all pretty sensible in my view. The truth bounds are applied to both individual atoms, such as the student is in class, as well as formulas. And so inference is essentially ensuring that if I have both of these things in the logical language, that there has to be some element of consistency between them. So if you flip those two, if you flip the intervals around, so the second one was the in class had an annotation of 0.9 and 0.1, we could then say that either of those individuals has to have at least that bound or something tighter. It can't possibly be looser. Outputs are truth. So inference, the outputs are value bounds assigned to formulas or atoms. So what you can think of inference as running is I have a bunch of formulas and individual atoms. Everything maybe gets assigned with some initial values that come from data. So things I actually know about from like some sample that my system observed, and everything else just gets a 0, 1, and I run inference, and inference tightens and tightens those intervals on all my logical constructs. And so if I care about a specific formula, it doesn't have to be a single atom, but if I care about a formula, I can just throw that formula in the original logic program with a 0, 1 interval, and it's going to just squeeze tight and tell me, how true that formula would be with respect to the rest of the knowledge base. So of course, that's very powerful because you can start to think of, oh, what if I'm doing some kind of classification test? Well, if my class label is associated with a single atom, I just make sure that that's included in the knowledge base, and I see what happens to those confidence values.
So is this updated with like gradient descent?
Yeah, we'll get into, so the way to think about this is we have a logic and we have an inference algorithm on that logic. And you can think of that inference just like we talked about in the logic class. Like we use a fixed point, they have something else that's actually a lot like a fixed point. Then you have an equivalent neural structure that's used to do training when you have real world data. Once you learn that structure, you use their inference algorithm. You don't use the neural net to do inference. I guess you could, but the algorithm, it makes a lot more sense. And you can continue to use that algorithm for inference after the model is trained.
So the neural net is only to get the weights of that particular thing.
The neural network is only used to get the back propagation. But in the forward pass is used to inference. So the outputs are that. So all the formulas you care about, Now, with the formulas, with every logical element, there is also a weight and a bias. And the weight and the bias are associated with the logical operators. So since we're not using classical operators, we're not using, and or that just gives you a binary answer, it's giving you a numeric one, it's changing these bounds. We then use function, and we'll talk about what we use for that. But they're essentially using fuzzy versions of and or in the quantifier. Each formula is going to end up having a different weight assigned. They have some results showing that this bias, there's a way to assign that where you don't, where it's just related to the weights. So it ends up being not an extra parameter under certain assumptions that I think are reasonable. So inference. So inference is a set of formulas, initial truth bounds for each atom and formula, and then you have that bias and weight that comes from the training that says how things are combined. The output is the final truth bounds for each formula and atom. So reasoning is done with this upward-downward pass. This is not forward-backward that is being used in training. Upward-downward is inference here, okay? So that's why they use those words. And the way this works is in each upward-downward pass, you could think of as weights are propagating through the semantic tree of the logic program from formulas to atoms, and then the other pass going atoms to formulas, and that goes iteratively until convergence. Yeah.
So the output is not really a chain of, it's not like it's still separated by each type. It's not really assigning probability to the whole thing that it computed in a sense.
I don't quite understand. There's still a chain of logical reasoning. No. We'll show why it's a chain of reasoning.
No, and what I'm saying is that you're saying that the output is the final truth bounds for each formula, but I mean, what I was asking is
Could someone has a hot mic, could you please turn that off?
So in a sense, we're only interested, it's still not enough, the chain of these conditions, but it's still individual conditions themselves. Makes sense.
So I put it another way, so everything that gets concluded, so when we talk about the fixed point operator, okay, so if I had a logic that had annotations, I can arbitrarily add in facts for every ground atom with a 0-1 interval. And it would make no difference, right? So where the fixed point operator I showed you, it looked like it was adding things in. You could think of it actually as assigning a true false to every possible atom. This is doing something similar. It's assigning a bound to everything. But what is nice about this is if I have a formula that I'm interested in, so I'm interested in looking at condition A or B, and I want to know the bound of that, I can put that in my knowledge base with an interval of 0-1, and it'll just tighten the bound for me through the inference process. I had one online, I think. And then I'll get the other question. Did we have a question from online?
No.
Yeah, can we talk more about convergence, how we converge?
For inference?
Yeah.
Oh, we'll talk, I got the slides, we'll go into that. Okay, so the basic setup for learning, and again, I labeled this basic setup. We'll get into details. But I just want to preview a little and kind of have you understand the roadmap here. So the neural architecture is directly derived a priori from the formulas and how they relate to each other in the syntax tree. So this is not inductive logic programming. We're not going to learn new logical formulas from the training data. That'll come back later in the course when we talk about differentiable ILP. And there's also an ILP extension of this work that came out earlier this year. Historical inputs and outputs, they're used as essentially training samples. So you could think of your previous ground atoms that were all true at the same time, essentially a world. That is what that was. So loss function depends on two things. One is mean standard error or whatever other common loss function you use. I think in this work they use only mean standard error, but that's not a huge deal. But also the number of inconsistencies. So the inconsistencies are for everything that's in your knowledge base. If the inference process ends up with L being greater than U, as a result, that's an inconsistency. So when I run my training samples through the forward pass, I'm evaluating that training sample on two things. One is, my error metric, so MSE. So I had some ground atoms that were maybe, were classifying activity in a picture. Was the person running or was he driving? Okay. And so I have a ground atom for each. So seeing if I got those ground atoms set correctly. And because they have intervals, they have this threshold value alpha. If it's assigned with an interval between alpha and 1, then we're saying it's true. Okay. So that's the error part. The second piece is that same training sample that gave me the yes or no to the ground atoms I care about, did it cause inconsistencies? And so now I look at all the resulting bounds from everything in the logic program. And I see how many of them is L greater than U. So that means it's inconsistent. That should never happen. L should always be lower than U. That's why it's called lower. So the functions used to combine formulas. So remember, we're talking about fuzzy logic. So we're doing things like the Lukashevitz T-norm and this kind of stuff. Okay, they have to be weighted. So we have to have weighted versions of these co-norms and T-norms. And they have to be differentiable with respect to those weights. And on top of it, as a side thing is, with those weights, they should still function like classical operators if you get classical input. So if I give you only atoms that are annotated with 1, 1, and 0, 0, the output of that operator, if it's A11 and B11, the net should be, that should also get a 1, 1 as well. Nothing else. Not some 0.91, not something crazy. 1, 1 should be the only answer. So the operators have to have that capability. Where they have room to play based on the weights is the shape of that curve on how it gets there. And so, yeah, so the forward pass is done with the inference algorithm, which is, a lot like a fixed point operator. Go ahead.
So, you said that the neural architecture is dependent on the logical requirement that we have. So, does it change every time we change the architecture?
So this is a really great question, okay? So the question is, for those who didn't hear, does the logical structure change, causing the neural structure to change if I'm adding in additional things to it? And in many ways, this is a little bit of a, can be considered a little bit of a shortcoming, because let's say I train my model to answer a certain problem. And then I come up with a logical formula. I think this is really important for a new problem. Now, I can take the thing I learned from the first problem, and I can use it with the forward-backward algorithm in this paper to answer the second. But there's no guarantee it's fit to the historical data for that. Because assuming that that formula that I'm now interested in was present in my historical data, I can actually compute that ground truth, and I could actually train the model to come up with different ways. So that's a great question, thank you.
I might have missed something, but since the upward downward pass is different from the forward backward pass used in gradient descent, why is it necessary to have some of the combination of the functions to be differentiable?
The upward downward pass is replacing, is the forward pass of gradient descent.
Oh,
Yeah, it's just within the forward pass, there's upward and downward. And so that goes to convergence for every iteration of gradient descent.
oh, okay.
Yeah, the backward pass you still need, because that's what uses the neural structure, that's what's used to learn the weights for backward.